Okay, everybody, I've started the recording. Welcome to our instructor training class meeting for Routing Switching Essentials Spring 2018. Appreciate everyone being here. Like I said, it is really good to see this kind of participation, especially with the beginning of classes. Hopefully we can keep it up. I am going to try to have weekly meetings. I know there are some weeks of travel that will require me to move meetings around and do some things a little bit differently, but for the most part, our meetings will be on Mondays, and I should be able to keep these meetings pretty easily because I think most of my travel entails traveling Tuesdays through Fridays or Wednesdays through Fridays in this coming week or this coming semester. You will notice if you do not have a microphone, you can type into chat. I think many of you were in my last class. Has anybody in here not had the introduction and needs me to go over the base introduction again? I think, Keith, you were in the last class. I think everybody's pretty much been in the class, so you know now how you go into modules. And by the way, everybody in here has done the first assignment in Moodle, so that's wonderful. Thank you very much. Every one of you are in the class, and I believe you've already begun to get started on work, obviously. Be aware again, even though there is a syllabus in Moodle, your actual due dates are from the calendar in here. So when you look in this, you don't have to really go to the calendar. You can just look right here inside of Netacad and see when these are due. You'll notice that different chapter labs, configuring basic router settings. Folks, this is something I start telling people when we get into the second, third, and fourth class, especially the second class because there are a ton of packet tracers. If you do not get all the packet tracers done as we move through this course, if you do 2 packet tracers per chapter, I'm not going to have a heart attack. You are obviously going to do yourself a much better service by doing all of them because then you know what your students are going to do. But the one thing that is non-negotiable are the hands-on labs. The labs that are in NetLabs that are actual hands-on labs, such as this configuring basic router settings, you must do all of them. So I'm going to go in here and schedule. Oops, my session terminated. I'm going here and schedule reserved in learners, and your class is ITC Spring 18 RSE, and Curtis, you get to be the guinea pig. Lab 1146, and you'll see now, look, all these reservations are taking place. You'll see all these people who've started using reservations. Now, I'll have a talk with Clarence. I don't know who his instructor is, but I don't like to see overlapping reservations like this simply because you can't be in 2 reservations at once. What'll probably happen though is Clarence will finish this reservation and then he will end it and then use this reservation, that's valid. But I'm gonna schedule right here. Now notice one of the things I do want you, as I've said in the orientation, you don't just have to schedule for right now. If you know you've got time on Saturday and you've got time at 9 o'clock Saturday night, you can schedule the pods. You'll notice even the next day, very few people have things scheduled out, a couple days in advance. So if you kind of plan ahead, you'll have access to the labs when you need it. No, somebody's already scheduled that while I was doing that. All right, so I'm gonna do a quick reservation right here. Again, remember this is real gear, so it takes about 5 to 10 minutes for it to boot up. So we'll let that boot while we're talking. Inside of here, again, you've got your launch, your chapter, you read, and then you complete the packet tracers and upload them. And again, the same thing with the documents here. Now, one thing I do want to ask you to do, and I'm going to open up, let's see if this is the PTO one. That's not it, that's investigating. Oops. That's bad when you click the same thing twice. Get back to module. Oops, that won't do it either. I know this makes a riveting video. I will find one. That's another one. All right, I'm going to cheat. Just go forward. I know this one's going to have it. All right, so here we got configuring IPv6 static and default routes. You will notice that on this particular packet tracer, when I open it up, This is a packet tracer that has you doing actual configuration tasks inside of PT. So it gives you a network, and I'll pull it over in just a second. It gives you a network, and it also gives you tasks that you need to do. And so you'll go down here and it will tell you, examine, look at the topology, and it says enable IPv6 routing on all routers. Okay, so that command, by the way, you will learn. All right, so it says config tag is locked. So what I'm going to do here is actually, CLI, go to CLI. All right, config T IPv6 unicast routing. You'll notice I should get some points, I hope. Maybe I don't do it until I get all of them actually configured with that. But this is one of the ones that you will actually get points for as you do the lab. Okay, and in this case, it's not giving you points for that particular item, but it is something you have to do. But you can do check results and see what you've done correctly and incorrectly. This is just looking at the routes, not that. So when you get finished with this particular packet tracer, I do want you to save it and upload it with your name.pka, but I also want you to take a snipping tool and show me your score and upload this picture. So you can file, save it as a JPEG, and then you can just upload that along with your .pka file. You will find that when you're grading these with your students, it saves you a ton of time when you do this. It also makes it easier if you see they miss something, then you can actually open the PKA file up and go through and find out what they missed. So it makes it much easier for you than having to, once they're uploaded. If you don't do this, what I have to do is I have to open every single packet tracer that's uploaded, open them up, do check results, and then see your results. If you have trouble with one, feel free to put down that you're having trouble with it and upload it and tell me what you were having trouble with, and I will go in and check it. Some of the packet tracers, I will tell you, are very finicky in that, for instance, if it asks for you to name a switch capital SW1 and you do lowercase SW1, it will not count that as correct. Also, there's a couple of places in this particular semester where they're asking you to put in a username, and it's wanting a username with a privilege level and some other things. So just be aware that packet tracer can be pretty persnickety about what you put in and how it's put in. Are there any questions about the base format of the course? Any questions about how NetLabs is going to work? Now, again, remember in NetLabs, when you're in here, you want to use the document that is inside of NetLabs to do your labs with. This has been changed to make sure that it matches what is in NetLabs. And one of the great things about this, like I said, one of the reasons I love NetLabs too is you can just click right here, and lo and behold, you've got a fully functional PC that is mapped to the correct VLANs and is mapped to the correct port on the switch. And then you can go in and make changes on it, which is not something you can do inside of Packet Tracer. Packet Tracer has a fake operating system which doesn't have the actual interface of a real PC. So we can go here and change adapter settings and do all the stuff we have to do on a normal PC. Okay.
I do have one quick question.
Shoot.
All right, so piece quick. In NetLabs, I'm glad you asked. You covered the one about the show lab content because I did find that it was different, so I got that one. But also, when we finish with NetLab, I normally go in and save, click the Save tab, and I save like what I've done. Is that necessary, or should we just click I'm done and log out?
Just click I'm done. Just click I'm done. The only reason you'd want to save it is if, let's say, you didn't get a lab completed and you wanted to save all those configs so that you could come back to it later. If you've completed a lab, one of the nice things I can do, and I'm going to use you as an example if you don't mind real quick. But if I look at my fall 17 class, I believe you were in there. Okay, so I can actually go in and look at a lab that you've done. So let's say I'm just going to grab, let's just do a simple one. Viewing the switch mic table. I can actually go in here and look at everything that you typed. So I don't need you to save anything for me.
Okay.
So I can actually go in and look at it. That's really one of the things I love about NetLabs is the fact that I can see everything that you type And then if you're having issues, many times I can go in here and say, oh, well, you mistyped this command, or this is a problem, or whatever. So it's pretty neat the way NetLabs works. So as long as you complete the lab, don't worry about saving it. Just click I'm done. If you are if you do want to, like, you haven't finished the lab and you want to come back to it, that's when you want to save it, and then you can reload those configs. Honestly, what I do though is I just copy those configs out to a text file and just schedule a new lab later, and then that way I can do it pretty easily too.
Okay, thank you.
Any other questions about NetLabs? Any questions about Moodle? You know, in Moodle, all I ask you to do is do that first assignment, and then the other thing I ask you to do is every week or two, just log into moodle.stella.edu just to prove that you're actually, quote, attending class, even though I know all of our work goes through NetAcad. We're doing all the work here. Okay. Here's all your due dates. Yep, go ahead. Is there a question? Nope. Okay. All right. All your due dates again are listed, so you can see them here when things are due. Please remember, just like the first class, and those of you who are taking 2 classes at one time, we do not have set in stone due dates. Hold on one second, folks. I'm a popular man today, it looks like. But the due dates are not something that I'm going to give you zeros if you don't make the due dates, okay? It is a suggestion. I have learned through teaching these classes many times. I've tried to do the classes without due dates, and half the class will say, well, what are the due dates? The other half is like me and is like, thank goodness there's no due dates. So I found, though, that the other half, like me, if I don't have due dates, then I never get anything done. So it's very important that I at least put some due dates in there to give you something to prod and to be trying to get to, okay? But if you are a day or two late on one of the labs, or even a week late, I am not going to have a heart attack. Just try to work ahead or try to stay caught up, because many of you who took the first class know how hard it is when the class ends and you're trying to catch up and you've got a whole lot to do. I do, however, understand completely that you are working full-time and that you have a full-time job, 40 hours a week. With that, let's start some of the most interesting and fun parts of the Networking Academy, in my personal opinion, and that is talking about routing and routing concepts, getting down to what really happens at layer 3 of the OSI model and how we move from one network to another. Now, one of the things is talking about maps. A lot of times we don't do these activities in this class ourselves, but this is a good activity for your classroom to have time to have students do a map and then go in and talk about how a Google Map route is very similar to how traffic flows across the internet, because it is similar in that you have to find the path across multiple possible paths. Now, when we look at networks, obviously we're back to our characteristics again of topology, physical versus logical. Those of you who are taking both courses concurrently know this is something we just talked about. Speed, cost, networks aren't cheap, obviously, and the more redundant and the more reliable they are, the more expensive they are. Security, availability, scalability, and reliability. All of those are key components of a network. Now, why route at all? The biggest reason is networks are broken into logical sections. These logical sections use logical addressing, and in the case of our networks, those are logical IP addresses. So there has to be a way to find your route from point A to point B, or from network A to network B. That is accomplished through routing. Now, routers aren't anything magical or super special. They are just computers. In fact, if you take a regular PC, put 2 NICs in it, load Windows Server on it or a Linux, load the correct software, IP tables, and some other items on there, and then also load on Windows routing and remote access, or think it's RSE, or it used to be called RSE. I'm showing my age. But you can make a PC into a router, no problem. The problem with that, though, is a PC is not designed from the ground up to route. In other words, you're going to learn that routers take packets apart, at least up to layer 3, in order to see what the destination IP addresses or IP network is. Then they have to put the packets back together, and so they don't decrypt, they deassemble, and then they reassemble these at each individual hop. They also have to do lookups inside of a route table. Specialized ASICs, application-specific integrated circuits, are used inside of routers to make them able to do this packet disassembly and reassembly and these lookups faster than just a pure computer. They also strip away a lot of the things that are not needed on a computer, and therefore reduce the attack surface area on them. But a router still has a CPU, so it has a brain, it has memory and storage, it has different types of memory we'll talk about. We'll talk about RAM, ROM, NVRAM, and flash, and some do even have hard drives. And then it has an operating system. So first thing we'll talk about is the memory that is on a router. A router has, first off, read-only memory, and that ROM memory is where you find a basic boot up or the post instructions, so power on self-test instructions. It also has what's called ROM monitor mode, or RMON. If you ever end up in RMON mode, you've got a router that can't find its IOS, its Internet Working Operating System, or Internet Work Operating System, and it's running off a very limited feature set. But ROM memory cannot be deleted easily anyway. It is read-only memory. It's permanent storage. Non-volatile memory, NVRAM, is also permanent storage, and that's where the startup config file is located. You need to know what's located in each one of these for the test for the ICND1, because they will more than likely be testing on this chapter and on that test. Can't tell you what's on it, but if I would know about it if I was you. Flash is where the iOS is. By the way, the easiest way to remember that is S, Flash, and iOS. Okay. There are some other system-related files there sometimes, depending on what kind of software you're running. And last but not least is your RAM. Your RAM is kind of like what I call the counter space in your kitchen. It's where you do your work, and when you're done, you're supposed to clean it off and it goes away. Same thing with a router. A router boots up, it loads the iOS out of Flash into memory. It then loads the running config, or it's got a running config running there, and it's got a routing table, ARP tables, packet buffers, all of that sits in RAM. When the power goes off, every bit of that goes away. You lose it. So again, I compare that to the workspace in our kitchen where we prepare our meal, cook it, and then clean it off. I compare ROM and NVRAM more, I'll compare Flash and NVRAM more to like the pantry where we put things for longer term storage, and then really there's no ROM comparison in the kitchen. Here's the back of a 1941 router. You can see that there are a couple WIC slots. These are slots where you will have WIC 2Ts or a WIC, different types of WIC, could be an Ethernet WIC or whatever. You've got multiple flash card slots. This is where you can put your flash. And then you've got different ports. You've got a console port. Now, I don't know if I got a console cable in this in my office right now or not, but I'll bring console cable in here and show you. But one of the things that you've got used to be every time you bought a Cisco device, you would get a console cable. They actually don't ship them with them anymore. That's a thing to remember when you start buying Cisco gear now. You do have to actually buy the console cable as a separate item, which is kind of aggravating. But there's an RJ45 connection with a horrible, ugly Carolina blue color under it, and the same thing for the USB. I went to NC State, by the way. Any of you from North Carolina know that Carolina blue is just absolutely abhorrent to us. So there's a Carolina blue cable that you can plug in here and then connect it either to a USB to serial connector or directly into a serial COM port if you happen to have one on your computer. There's an aux port, which is traditionally used to connect via reverse telnet to a modem for dial-in. It's also a very handy way to break into somebody's router if they haven't forgotten to secure that port. And then there's 2 Ethernet interfaces here, and then there are USB ports, which depending on what iOS version you're using, can serve multiple purposes. A lot of times, especially now, for a long time they had the USB ports and they were not enabled, but now you can actually upgrade to iOS. You can move files across it and all types of things using the USB. But this is just a specialized computer is all it is. It's got a power supply, it's got a CPU, it's got RAM, it's got ROM. Nothing about it is all that spectacularly different from just a regular computer. But routers connect networks and they make routing decisions. Now this is a hilarious example here because there's only one way for this thing to go. Okay? Not much of a decision here. Neither one of these routers has to be very smart, because if you want to get from this LAN to this LAN, there's only one way to go, and if you want to go back the other way, there's only one way. Now, here's where it gets more interesting. When you start connecting multiple networks with multiple paths. Routing, and we're going to talk about static routing, and we're going to talk about dynamic routing. But those 2 types of routing, we will discuss how with static routing, you specify manually the direction that information should go. And then with dynamic routing protocols exchange information between routers and then use items called metrics to determine the best path between. Okay, Penny, that's no problem. And Penny, if you need to leave, that's no problem. I will put this on YouTube. So routers choose the best path. Again, this is not much of a path, determining path, but you can see here that in this case it's got connected, and a static route. There's a static route going to the 3.0 network, which should be this network over here, which I've actually got a typo. Okay, that should be the 192.168.3.0 network. You'll see that it's connected locally, and so that makes the routing decision. Now, there's a couple things about routers. Routers make their routing decisions based upon their routing table and their routing table alone. In addition, just because there's a route to the destination doesn't mean there's a route back. All right, so that's something to keep in mind as you think about routing, because I see so many times students put routes in and then there's no route back and it doesn't work. And they go, well, I got a route. Yeah, but do you have a route back? All right. Now, inside of a router itself, there's a couple ways that packets can be switched. Now, don't get confused. I know a router is a router, but it still switches packets between interfaces. In other words, it brings them in, makes a decision, and then switches them from one ingress interface to an egress interface. There are 3 major methods that we use inside of the control plane on a router. One is very old and very inefficient, and it's called process switching. With this method, every packet that comes in has to be passed up to the control plane, a routing decision made, and then it's sent out to the egress interface. No matter what, even if every one of these packets were going to the same egress interface and they were destined for the same network, every one of them would have to go up and be handled by the control plane. That is very, very inefficient. The next method that Cisco developed was called fast switching. What it would do is it would create a fast forward cache. And when the first packet went through and a lookup was made, it would then take that lookup and put it in the fast forward cache. And for any other packet destined for that network, it would send it out that egress interface without it having to go to the control plane. All right, much faster and efficient. Cisco said, hey, we can go one better. Let's do Cisco Express Forwarding. Now with this is how it happens. Once you get all your networks up and going on the router, and you've got all your routing sources, Ceph creates a forwarding information base, okay? It then also creates an adjacency table. And what it does is it calculates all possible networks that you could possibly route to on this router. And it calculates the egress interface, so that any packet that comes in doesn't even have to go up to the control plane, because the control plane's done all the calculation and put it into the the fib and the adjacency table and uses that to send it out the egress interface. Now here's the best way I think to kind of think of this. Process switching solves a problem by doing long math even if it is the same problem. So no matter what, it's going to do the same thing over and over, even if it's for the same destination. Fast switching solves the problem by doing the longhand math once, then remembers the answer and uses that for anything that's an identical problem. SEF solves all the problems ahead of time and then puts them into a spreadsheet so it can be used to be looked up whenever the question is asked. So you've got process switch, fast forward, fast switching, so process switch, fast switching, and Cisco Express forwarding. SEF is what almost all, well, it's what the modern Cisco switches use, Cisco routers use, and any layer 3 switches. Questions about those? All right. Router components. Let's see, start a config file. That should go in where?
Run RAM. No, you said start a config file. That's going to go in your NV RAM.
Yep, and my flash is not working.
I know, I had the same problem this morning.
So NV RAM would be the startup configuration. What's in flash?
Your iOS system.
iOS and system files. What's in ROM?
Diagnostics and boot instructions.
Yep. And running configuration will be in RAM, right?
Mm-hmm.
Okay. Now, one of the things I'll show you, you've now seen this twice in the curriculum. If you see it twice, you know it's probably going to be on the chapter test. If you see it 3 times, you know it's probably going to be, yeah, you're going to see it again. There's a couple labs, and then we're going to go connecting devices. We're going to look at connecting actual devices onto the network. Now, this is something that is one of the hardest things for students to get for some reason. The concept of a default gateway. The default gateway is the IP address on the router interface closest to you on the same network. So you're never going to have a default gateway that is on a different IP address than what IP network than what you're on. Okay. Now, here's something very interesting too. This is the process, if you remember from our intro class, the process of proxy ARP. Remember, this machine PC1 needs to contact this web server. But when it sends out an ARP request, that broadcast goes out here, and it's an ARP request for a remote host. So the router will proxy ARP its MAC address for the destination MAC address. Okay. Now, the source and destination IP addresses are still the 110 and the 199. That will go to this router. This router will make a route table decision based upon what's in its route table. It will then send it over to this router, which will strip off everything up to layer 3, make a route table decision, then reassemble the packet and send it over here, and it goes over this way. Just remember, just because there's a route going this way does not mean this router here knows how to get back to this network. So this is a great picture here showing default gateway, showing proxy ARP, and showing source destination IP address. Now here's an example of documenting network addressing. So you could do, you need to document it, put down what the IP addresses are, and also you could do, if you did trace route or those types of things, you could see this, or you could ping across. Enabling IP on a host, this is just going in and putting an IP address. So you can do it statically by putting in an IP mask, subnet mask, and a default gateway. Can anybody remember what the purpose of a subnet mask is?
Can I? The subnet mask tells the number of bits, number of network bits, and an IP address, and it masks the host portion with zeros.
That is correct. Yep, the whole purpose of the subnet mask is to tell you what portion is the network and what portion is the host. It puts ones in the network portion and zeros in the host portion. Very good. So we've got statically assigning an IP address on a host, and we can do DHCP, dynamic. And we learn how to actually do DHCP later. Here is device LEDs. Here's what I teach my students. Green is good. Anything else could be bad. All right. Now, one of the things I also teach my students is learn your particular devices. So in this case, they're showing you that if the gigabit zero speed is 3 blink and 1 pause, it's a gigabit. If it's 2 blink, 1 pause, so this would be dependent upon what device you're using. So be aware of that. I will tell students many times, I'll go and look at a problem and I'll say, well, you don't have a link light. And they'll find out they plugged the wrong cable in the wrong port. You know, I always tell them blinky lights. If you don't have blinky lights, you probably got a layer 1 issue. Here's console access, how we actually get into a router or a switch with console. I use PuTTY. I think a lot of people use PuTTY or Super PuTTY or Tab PuTTY. There's all different kinds of PuTTY. But you take an RJ45 to DB9 console cable from a serial port and plug it into the console port on the router. So you can actually take this ugly Carolina blue cable, stick it in the serial port, and then plug that into the console. Open up your terminal emulation program, and then set your terminal settings. And I'm pulling up PuTTY on my machine here. It's taking forever for PuTTY to load on the desktop. So I can go in here on PuTTY. Go in here on PuTTY. I can go down to my serial and I can do COM1, 9600, 8N1. One of the things I will tell you, if you're using a serial port, you can usually get along with flow control being X on, X off, even though the recommended thing is none. If you're using a USB, the serial connector, I've had a lot of trouble when people accidentally left flow control on. So make sure it's 9600 8N1, no parity, no flow control. Then if you had that connected to a device, you can click open, and it would then open the CLI from the console. So you're doing, this is called out of band management, because you're not going across the network to manage your device. You're plugging in physically to the device. So you're out of band management. This is an example of how you can use PuTTY with your COM 9600, and then you can set your serial 8N1, click open, and it would open up a Cisco device. Now, enable an IP on a switch. So if you need to put an IP address on a switch, this is a review from our intro class. You go into the switch, you put it on interface VLAN 1 or whatever VLAN interface you want to use for your management. You'll learn, I really don't like them using VLAN 1 at all for this, because you will learn in the real world, never use VLAN 1 for management, because all ports are in VLAN 1 by default. But they will let you do this for, just to learn how to do it, and then we'll move it off as we move forward. So, but you go to VLAN 1, put an IP address on it, do a no shutdown, and then you need a default gateway so that this switch can get outside of the network if you want it to be able to do that. Then, of course, you need to do a copy run start. This is something that's new. I don't think we actually had these in the intro. If we did, they were very minimal. But this is going to ask you to configure the VLAN 1 interface on S2 using the second available address. Make sure to activate the interface. Okay. So second available. First off, here we'd have to do interface. We do int VLAN 1, and it's saying, whoa, that's not working. That's because on these particular items, you have to use the entire command. Otherwise, it will not work. So there are no shortened commands here. You have to go in and put the entire thing, which is very aggravating. But the good news is it teaches you to use the entire command. All right. Even that, I can't do no shut. So it's pretty aggravating, but there it is. Okay. If you don't know how to do something, you always click show me, and it will actually then do show me. It will show you. Okay, basic router settings. What do we need to do on a router to get basic router settings? One is host name. Okay, so just go into global config. Remember, hopefully you remember this. If I'm on a router and I'm sitting at this prompt, what mode am I in?
That's your user exec mode.
Correct. That's user exec mode, which means I can
Basic diagnostic.
look.
Oh, sorry.
Go ahead.
I was just saying you can just basic diagnostic testing.
Yep.
You do like show version, I believe.
Yep. Basic diagnostics. Diagnostics. You also, I call it the look, but not configure. You can do some looking, but you can't do a whole lot. Now, to get from this mode, from user exec mode to privilege mode, what do I type in?
EN.
EN or enable. The full command is enable, and that will take you to this prompt, which is privilege. Exec mode. And this is pretty much, this is God mode. You can do anything. Full control. Okay? And then you can also, obviously, from there go into, type in config T, which is short for config from terminal. You get into your router config mode, which is global config. Okay? So these modes are still there, nothing different. Okay? So we're going to global config, put in a host name. You go into the create a secret, enable secret class, which will prompt you for a password when you type in enable and go in from, or transition from user exec mode to privilege exec mode. This is line column 0, putting in a password and requiring login. Same for line V2I 0 through 4. And then this service password encryption encrypts the passwords for inside the running config and the startup config with a pretty insecure form of encryption, but at least it will keep someone from shoulder surfing and seeing your password. So again, host names, passwords, a banner, IP addresses, you're saving configs. I would say IP addresses on the interfaces, and then that's going to be your basic config. Okay. Put your IP addresses on the interface. You open up the interface itself. Descriptions are optional, but they're not bad to have on your devices. They're like comments or remarks that you kind of have, especially when you're doing a circuit out to an ISP. It's good to say, link to description, link to AT&T circuit 4710 or whatever. IP address, no shutdown, and that brings it up. Remember that the difference between a router and a switch is that a switch's ports by default start out on and available. A router's ports start out shut or administratively shut down. So you do that for each interface. And as you're bringing each interface up, one of the things you will notice, something we haven't done is routers do have DCE and DTE links. If a link in the lab is shown as being DCE, it means it is a data circuit terminating end, which means it is a clocking end. In the real world, we connect, it depends on our device. Sometimes we have built-in TSUs if we're using, T1 circuits or T3s or whatever. So much is Metro Ethernet now, we don't really have to use a lot of this, but if we're connecting to a circuit that needs the clock rate, most of the time now we've got a built-in TSU we slide into the WIC slot, or we may have an external TSU. If we have an external TSU or CSU DSU, it provides clocking. We don't have those in the lab. So in your lab, you have to connect cables back to back, a DCE to a DTE end. And so the end that is the DCE end, you have to put a clock rate on. That's so it can simulate that there's a CSU DSU there. Let me pull this over here just a second. Any of you seen a CSU DSU before? Guess not. All right. here is a common older, this is very old here, but here's a common older CSU DSU. You've got the RJ45 connection going out to the T1 circuit, all right? There's a V35 interface on the CSU DSU, which is providing clocking. This provides clocking. And then that V35 cable comes over to the router, and this is a DTE cable because you're coming from a DCE device to a DTE device because the router is not providing clocking. It's very difficult. And here's an example of a TSU, or internal CSU DSU, which is just a WIC card that's got it built in, and you configure it using your internal commands. It's a DSU that's built in. Nice thing about that is you don't have to have, you know, a power supply for the CSU DSU or rack space for the CSU DSU. By the way, any of you got any of the new 4321 routers in?
No.
They have an external power brick, and I do not like it. I understand why they did it so they don't have so much component on the inside, but it's pretty aggravating that they've got an external power brick. These are all examples of older CSU DSUs. Adtran made most of them, or made a large number of them. But we don't have these in our lab. So when we connect two routers together, what we do is we take a DTE and a DCE cable and hook their V35 ends together. And on one side, we put a clock rate. So in other words, this cable would be connected to a DTE cable. R2 is the DTE, R1 would be DCE, and we fake having a CSU DSU, excuse me, a CSU DSU in here by putting a clock rate on R1. As you do the labs, it'll make sense. Be aware that in your actual classroom, you're going to need to connect DTE and DCE cables back to back to make that work. IPv6, just like IPv4, folks. You go in, you put a static IP address on the host, you go into the router, you put IPv6 address. It's pretty much the exact same nomenclature as what you use for IPv4. You just do IPv6 and you put it on there. Okay. You do have to do no shutdown if the interface has not been issued a no shutdown command before. If it has, you only have to do it once. Now, this is a strange little beast here. A loopback interface is a virtual interface that cannot go down. Once you bring it up, once it comes up, once it has an IP address on it, it doesn't go down and it's always available. We use loopbacks for a variety of things. One of the ways we use it sometimes is to ensure a router ID for processes like OSPF and BGP and those types of things. We also use it sometimes for testing. So we'll bring up a loopback or several loopbacks, put networks on them, and then have those networks routed through a routing protocol so we can do testing. There's just a variety of ways to use loopbacks, but it is, like I said, a weird beast because you go into interface loopback 0, and I think the maximum number is about 4 million loopbacks that you can have on a Cisco device. But be aware that this is how we do it. Once we put an IP address on it, it behaves just like any other interface. You can shut it down, you can bring it up, but by default, when you put an IP address on it, it comes up. It will not shut itself down because a cable's removed, however. So that's one of the key things. You know, remove this cable right here on gig 00, and the 192.168.10 network, it will disappear. The only way to make the loopback network disappear would be by shutting down, you know, going into a shut command on the loopback. So this is a strange little beast there. So how do we verify interfaces? One of my favorite commands on earth is show IP interface brief. I know you're a geek when you've got a favorite iOS command, but that is one of my favorites, show IP brief. The only thing I wish they would add to this command is I wish they would put the /mask on it. I wish they would tell me what the mask is right here so I wouldn't have to dig any deeper to see what the mask is. This proves a couple things. First off, when you look at this, it tells you what IP address is on the interface, tells you how it was set. In this case, it is manually set, so someone went in and typed it in. The first item is your layer 1 status. The second item is your layer 2 status. So up means everything's working. up, down means layer 1 carrier signals are working, but you're not, something's wrong at layer 2. Could be data link layer encapsulation mismatch, or could be something weird going on a T1 link or something of that nature. You're never, however, going to see down, up. If layer 1 is not working, layer 2 is not going to work, okay? You will see down, down, and sometimes you'll see administratively down, and that means you just forgot to bring it up, all right? So this command is one of the first things I usually do when I'm troubleshooting any type of problem on a router. Just do a show IP at brief and see what's going on. Then you can do a show IP route, and that will show you the routes that are in the route table. Now, for a router, there should be a connected route for every network that you have placed on an interface and brought up. So you see here, you've got 3 different networks. Now, this L, or local, is the actual IP address assigned on the interface. That local is something that is new to iOS 15, and it will not show up here in older versions. But that just shows you the local, and it's the actual IP address on the interface. Show running config type, or show running config interface gig00 will show you just that interface in the running config, and it will show you the mask. You can also do show interface gig00, and it will do it. Okay. So those are good commands. If you want to verify directly connected interfaces, all you have to do is show IP at brief. In this case, notice that with V6, it is literally show IPv6 interface brief. So it's not like it's rocket science. Show IPv6 interface gig00, it will show you that, IPv6. Show IPv6 route, shows your V6 routes. So again, we're not doing anything that is drastically different with IPv6. We've just got longer addresses, as we learned in our first class. Here's some cool things you can do. Filter commands, you can do show running config pipe section line VTY, which will start with the section that begins with line VTY. So a lot of the same commands you'd see on any Linux system you can run here. Show IP at brief, or show IP at brief pipe include up will only show the up interfaces. Show IP at brief, and then show IP at brief pipe exclude unassigned. It would get rid of the unassigned or unset, anything that didn't have an IP address on it. Show IP route pipe begin gateway, show you that part of the IP route from there, and so on and so forth. So you can use the pipe command to do all types of things. You can do sections, include, exclude, and begin. This really helps when you get out in the real world and you've got a router config that's 200 lines long, and you don't want to have to sit there and just space bar through it. Command history, you can do terminal history size. By default, I believe it's 10. Yep. By default, it's 10 commands. If you want it to do more, you can actually do terminal history size 200. This will allow you to hit the up arrow to see the last 10 commands by default, or with this case, they changed it to 200. Pretty useful when you're doing, when you're working in the terminal. Now, here's an example of the router switching function, just like I talked about. At each individual router, it takes the packet up to layer 3, makes a routing decision, and re-encapsulates the packet in the correct frame format for what's going, the link between R1 and R2. Goes to R2, de-encapsulates it, re-encapsulates it, sends it out across the serial link in the correct format, so on and so forth. So at every single hop, it de-encapsulates it, makes a switching decision inside between an ingress and an egress interface, and then forwards it. Now here's where it's actually pretty good when you're starting to see some of the, I have a packet for PC2. Now notice, what path does it need to take? It ANDs its IP address with its MAC address, its subnet mask, and then it takes the destination IP address, ANDs it to PC1's subnet mask, and finds out the PC2 is on a different network than PC1. At that point, if it's configured, it sends it, well, first off, it's going to do an ARP request, and R1 will reply. It will then send it to the default gateway, and it will be sent to the default gateway for a routing decision to be made. So PC1 ANDs its IP address with its subnet mask to find out what network PC1 is on, in this case the 10. And then it takes the destination, which is 40, ANDs it to PC1's mask to find out that PC2 is on 4.0 network. And then it knows then that it has to send it to the default gateway because it's not on the local network. And now you'll see it forward it to the next hop. This is just walking through, and I'm going to let you do this on your own, but you'll watch it actually go through and change the MAC addresses. Won't change the source and destination IP addresses in these cases. It's just going to change the data link information. Okay? So it pulls up to layer 3, looks for a routing decision. Okay? It's 2 hops away over at 2.2, so it makes that decision, then it re-encapsulates or rebuilds the frame, and then sends it out towards R2. And that continues on all the way till it gets to R3, and it reaches the destination. And then it has to do the same thing all the way back. Okay? I would greatly suggest you do this activity because it is a really good activity. So here is our routing decisions. Okay? Packet arrives on the interface. The router looks in the table for a match. Does it match the subnet of a directly connected interface? If yes, check the ARP cache if necessary. And if it's not there, do an ARP request. If it is, forward it to the host on the local subnet. If it is not destined for a directly connected interface network, then is it destined for a remote network that I know about? If the answer is yes, encapsulate the frame in the correct format and send it to the next hop. If it doesn't match a directly connected or a remote network, there's 2 possible things that are going to happen next. Is there a default gateway, or is there a static default route or a default route set on the router? If the answer is yes, it's going to forward it to the next hop, whatever that default route states. If there's no default route and it doesn't match any of these others, it goes in the bit bucket. And typically you get a destination unreachable ICMP message from the router. Now, how do we determine the best way to get from one network to another? Well, we do it by metrics. The best way to describe a metric to a student is to ask them where they go to lunch. When we make decisions about going to lunch, what are some of the things that we decide? Let's think about, do what?
How close it is to me.
Yeah, oh definitely. Closeness to campus, okay? How far away it is, what else?
How long is it going to be to get the food?
Yeah, speed of service, definitely. Quality of service. Cost is a big thing, yeah. Especially if you're a state worker like me toward the end of the month.
Is it available?
What else?
Is it available? Is it up? Is it running?
Is it open? Yeah.
Is it any good?
Yeah. Quality of food, yeah. Quality of food. I always say type of food. I love Mexican food, so type of food. What do you want to eat today? Guess what, folks? These are all lunch metrics. These are how we make our decisions of where we're going to go to lunch. How much time do I have? I don't have much time, so I got to find something close to campus. You know, it's got to be somewhere that's fast. I want some Mexican food, but what's the fastest one that's also closest one that's got good service with good food? All of those are metrics. Routers determine the best path based upon metrics. They look at links and they say, okay, my metric is hop count. Now here's something that is very important. Hop count is every router you go through counts as one hop. So in this example, if we were running a routing protocol that used hop count, such as RIP would think that the route from R1 to R3 to get to PC2 was the same as R1 to R2. Excuse me, take that back. It would actually think, look at this, it would actually think R1 to R3 was a better route than R1 to R2 to R3 over these T1 lines. Now, I will tell you, typically and on average, the path from R1 to R2 to R3, this should be much faster than a 56K link. But RIP, because its metric is not very complicated and its metric is not able to know differently, would think the better route was across R1, R3 to this network. So with hop count, it's going to go this way, which doesn't make a whole lot of sense. That's why RIP's not in use very much anymore. With bandwidth, it should go this way, assuming those T1s are operating at their correct speeds of 1.544 megabits per second. So cost versus bandwidth. So different types of routing protocols use different metrics. RIP uses hop count. OSPF uses an item called cost based upon the cumulative cost. EIGRP, you're going to learn as we get into the third class, has bandwidth, delay, and reliability. Bandwidth, delay, load, and reliability, but it really only uses bandwidth plus the sum of the delays. So routing protocols have different metrics, just like we have different metrics for where we go to lunch. Now, some routing protocols also have the ability to do load balancing. In other words, if there's links that are the equivalent of one another, they can send things across both links. Okay. EIGRP does support a thing called variance, which is unequal cost load balancing. OSPF will support equal cost load balancing by default. Again, that's something we'll go over much more as we get going down through the class. I'm going to cover AD, and then we'll probably stop here because I can finish up the routing table and everything. We'll do it next week. But administrative distance is a very interesting concept. Let's imagine that I'm trying to get from network A to network B. So let's go back one time here. I'm trying to get from here to here. And all of these routing protocols are running both RIP and they're running OSPF. Well, the routers all have two different ways of getting from PC1 to PC2. RIP would say the best way to get there is from R1 to R3, okay? And let's say this is a 56K link. OSPF would say the best way is to go around these T1 links.
Yeah, I'm not ready.
But now I've got two different routes from two different routing protocols. Which one of those two goes in the routing table? That is completely determined by administrative distance. If you look here, lower is better. So the RIP AD is 120. OSPF is 110. If these routers knew how to get from this network to this network via both RIP and OSPF, the OSPF routes will go in the route table because the administrative distance, which is a measure of trust, of how trustworthy a route is, within or between different routing protocols. So AD is between different routing protocols. AD will tell you that OSPF is going in the route table, RIP would not be used. Now look at this. This is all based upon Cisco's definition of what is more reliable. Why is EIGRP, which is a Cisco proprietary protocol, rated higher than an open source protocol like OSPF? And it's 90, which means it's better, more trusted than OSPF. Anybody know? It's Cisco's chart.
It's Cisco proprietary.
Yeah, it's Cisco's protocol and it's Cisco's chart. So they said, we believe that EIGRP is better than OSPF, so we're going to give it an AD of 90. So that its routes will be picked. So we go back here again. If all these routers are running both OSPF and EIGRP, the EIGRP routes would go in the route table. Likewise, look at this. If we put in static routes, guess what? They would overrule any dynamic routes. And the reasoning there is if a network administrator goes in and takes the time to put in a static route, then that network administrator wants the traffic to take that path. So metrics are used to find the best path within a single protocol. Okay? So when we say metric, finds best path within a single protocol, single routing protocol. Okay? AD selects most trusted routing source between multiple sources, such as static versus script, or static versus anything. Okay? So with metrics, we're finding the best path within a protocol. And then, if you're running multiple protocols, the AD is what determines which one of those two best paths would get put into the routing table. Does that make sense?
Mm-hmm.
Okay. What I'm going to do now is I'm going to stop the recording. I'm going to ask you to have